This first topic may look a little familiar to you because it's often taught in a beginning algebra course. We teach it in our elementary algebra course. But I want to review simplifying square roots. And so let me take a short example here. The square root of 12. And what can we do with the square root of 12? Well, the idea is to break it up into factors such that one of the factors is a perfect square. So 12 can be broken up as 4 times 3. So what is a perfect square? Well, 4 is a perfect square. Perfect squares are numbers which are squares of other integers. For example, 4, 9, 16, 25, 36. Those are all perfect squares. And so now if I had broken this up into 2 times 6, I couldn't have made much progress because neither 2 nor 6 is a perfect square. But since 4 is a perfect square, its square root is an integer. So the square root of 4 is 2, and my expression then reduces or simplifies from square root of 12 down to 2 times the square root of 3. Alright, so that is a simplifying process. And as I hope you realize by now, simplification is a very important process to learn in algebra because it allows us to take complicated problems and whittle them down to they're somewhat more manageable than we can solve. So it's an important algebra process. Now, as far as for computation purposes, it's not very interesting because now that you've got electronic calculators, as I do, then you would just punch in the square root of 12 and get a decimal representation. So if your only goal is to get a decimal approximation out of this, then by all means pick up a calculator. But in terms of algebra, since you're here to learn algebra, we also have to learn simplification. There was a time when, before calculators, when this was pretty critical because simplifying square roots or other kinds of radicals was assisted you a lot in calculating them. If you had to calculate these things by hand or look them up in tables, oh, it was a nuisance. I grew up in that era. And so, but now we can just use a calculator. Alright, so we simplified this square root, and the act of simplification is the act of factoring out an integer. Now let me take another one. Let's look at the square root of 27. And what is it? Is there a perfect square that can be factored out of 27? Of course, it would be 9. So 9 times 3 is 27. And the square root of 9 is 3, exactly. So I've simplified this one as well. 3 times the square root of 3. Now, in most integers, their square roots will not simplify, but many will. Many will. And that's what you're getting exposed to here. Now, I want to show you one reason to simplify. And I also think it's an interesting observation that you probably took for granted that what I told you was correct. It would be okay to multiply these square roots and get this number. Alright, you taking that for granted? Well, we've got to be careful about that. Is that really true? Well, it is. If you look at, in terms of exponents, 12 to the 1/2 power is the square root of 12, and that is 4 times 3 to the 1/2 power. Each of these is raised to first power, and so there's a theorem, the power rule of exponents theorem, which can be proven, demonstrates that we can, in a sense, distribute that power inside the parentheses. So it becomes 4 to the 1/2 times 3 to the 1/2. So I'm able to multiply those exponents. And now we get square root of 4 times the square root of 3. So we've been taking that rule for granted, but here's a justification, partial justification of that rule. Now, I went to that trouble to show you this because I want to contrast it with a false rule that some people misapply. And so Let's look at this problem. What is the square root of 12 plus the square root of 27? All right, so the unthinking math student will just add these together and get the square root of 39. And you can show on your calculator that square root of 12 plus the square root of 27 is not equal to the square root of 39. Not by any means at all. But actually, we're able to combine these terms together, because we saw up here that the square root of 12 is 2 times the square root of 3. The square root of 27 is 3 times the square root of 3. And so it's like having 2x plus 3x. We now have like terms, or like units. We have 2 of these square roots of 3's added to 3 of the same square roots of 3's. That gives us 5 altogether. 5 times the square root of 3. Alright, so now let me contrast that with another problem to simplify. What is the square root of 75? Well, if we factor this into a perfect square times something else, that would be the square root of 25 times the square root of 3. And what is that? That is 5 square roots of 3. So look what we have here. Coming back to here, it turns out that the square root of 12 plus the square root of 27 is equal to the square root of 75. Can you see any kind of logical connection other than through square roots between 12, 27, and 75? I sure can't. You know, I could not have just predicted that off the top of my head. And so that's why we've got to be careful about these rules. It's okay to combine a multiplication, and the same goes for division. You can combine those square roots, but you can't combine a sum of square roots into a square root of a sum. In other words, the square root of A plus the square root of B is not equal to the square root of A plus B. All right, so I've seen a lot of students make that type of error through the years. Even calculus students will sometimes make that error. So let's cut our losses on that.